Hey, what's up everyone? So welcome to my video where I will be explaining how I got my hash map library to work. So the hash map data structure, otherwise known as the hash table, is basically a list of entries on a large table that is distributed onto a number of bins. The number of bins are determined upon creation typically, and we decide what element goes onto each bin depending on the item's hash value, otherwise known as the hash code, and we determine the hash code from the key of the item. The key is typically sort of the identifier of the typical element that we want to add on to this data structure. We determine that by applying a hash function. That hash function will then do some sort of mathematical computation and give us a hash code. That hash code tells us like which bin. So for example, we might have a set of 10 bins, and then based on that value we know like whether to add it to the first bin, the second bin, so on and so forth. And this actually makes it better on retrieval. So here if we look at the function, we have one of the functions we have is hash map get. We give to it the particular hash map which we've created already, and we pass to it a key, which in this case might be, say, like the name of an employee. So for example, Max Guerrero would be the key, and we would then be able to retrieve the data. The data might be, say, like a table of my information, my full name, my age, date of birth. Say if this is for a job, then it might be like the name of the employee and their position, their salary, all that good stuff. So basically that's really two of the most important functions from this library are hash map set and the hash map get. Hash map basically says like, hey, here's the data structure, here's the item that we're trying to introduce onto this hash map. For example, it might be Max with my associated employee information, and we might, a computer program that's going to be using this might actually use this a lot. They might have a whole list of employee names and their respective employee information that will get inserted onto this data structure, and then at some later time we might want to be able to like extract information, say for another employee named John, right? We get John's information. We need to provide what name, right? That's the key. And then we will return, void will return to us the data, and then that data we can sort of interpret it based on the context of the application. So in the second part of the video, I would just want to say that if the first part of the video did not make sense, don't stress, as I will actually be going a little bit into more detail onto the inner workings of how to actually create this data structure, and into the inner workings of these functions into a little bit more detail. So hopefully that will make sense. But please keep in mind that this video is intended for people with already a decent command of the C language, and typically that will entail CS students and computer engineering and or some electrical engineering students. So that being said, so another thing is that you might actually realize, well, what is really the point of even this type of data structure existing? And the key advantage of using a data structure like this is that when we want to retrieve an element from the data structure, so for example, say I want to retrieve the information for the employee named Max, then you may have noticed that earlier in the first part of the video I said that we're going to be distributing all the data into bins. So if I want to retrieve Max, then all I have to do is get the hash code for Max, which Max we take as an input, and we apply that input to a hash function. The hash function will give us a hash code, which is just a new number that ranges from 1 to the number of bins. That way, if I have the number, then all I have to do is search within the index of that hash bucket. So we have like, say, 10 buckets, and Max gives us number 3. And if each bucket has, say, 100 elements, then I went from searching from 1,000 elements to searching to just 100 elements. So that is the advantage here, is that by us using this hash map, we are going to reduce the time we spend searching onto this database. And as the database is larger, and as we have to make many more calls to it, the gain in terms of us saving time that we can get from this in the long run is going to be like, well, in the previous example that I just gave, the hypothetical one, that's a factor of 10, which is great because a big part of software development is optimizing. So just keep that in mind as to sort of motivate us onto why we're even doing this, learning about this data structure in the first place. So as promised, let's go ahead and take a look at the code. So actually, I would encourage you, based on this header file, because the header file tells you what the function, what this library does at a high level, you should be able to derive the actual implementation for each of these functions that will allow the hash map to accomplish what it should do. So you can look, what it should contain is, it should contain a creation, which will return to you a type of hash map. The definition of hash map we will get into right now, but just think of it as the actual object that we will be, the data structure that's going to be written to and possibly read from. For each time we create something, we also want to destroy it, right, to prevent memory leaks. And for each element we want to populate onto the data structure, we want to be able to possibly retrieve that element in the future by using this hash map get. On hash map traverse, what this does is, by the way, I hope you can see my cursor. If not, I'll highlight it from now on to make things a little bit easier on your eyes. So hash map traverse, what it does is we basically, as an example, we might want to print out the elements, all of the elements. See, like, for example, we might want to see all of the elements in bucket 1. We want to see all the elements in bucket 2. We might want to see all the elements in bucket 3 in a sequential order to give us an idea of what the state of the current data structure is. And of course, we might also want to delete a specific node, a node being an actual hash map node. So that being the case, this is what it should do. Now let's actually talk about the elements, the sort of type defs, right? So first of all, we should, the most like infinitesimal element of our concern is the hash map node, and it consists of a key. For example, like say a node might be, basically a node is the object of interest, which in a particular application example might be the employee, right? And an employee's key, right, is sort of like, how do we identify what employee we're referring to? It's the string, which in my case would be like Max, and the data might be this data pointer might point to, like, say a data structure, a structure, not a like data structure, but like a structure which would contain, say, like my date of birth, the name of my position within the company, sort of like any sort of like promotions in the past, or any, all that stuff. And the hash would be like, what value does it have? So remember how we said that, like, for example, if we have 10 bins, when we were inserting that value, what was the hash number of that element? So say like Max gave 3, then we would set this item to 3. Now the next thing is sort of like at the next level, we have the hash map element. And the hash map element, sorry, not the hash map element, but the actual data structure itself. So when we create this data structure, we will create one of these guys. And nested within it, it will have the hash map hash, this is the hash map function from which we use to generate hash map codes. And this is hash map compare function, which is useful when retrieving. So like, if I want to search up, say, Philip on the entire data structure, I want to be able to compare, say, Philip to all the other items on the data structure until we have one that matches. So if Philip matches with Philip, then this compare function will return 0, and if it returns 0, that means we've got a hit. And if we got a hit, then we can go ahead and say, hey, yeah, the element that you're looking for is here, and here's the associated data. So that's why this is there. And this is the actual dynamic array, which we will use to represent the buckets. So we say, for example, here the default number of buckets is set to 5. Don't worry, you can set this to whatever you want. You can set it to 100 if you want, for all I care. And that means that upon initialization, we will create, say, 5 buckets, and each of those buckets will then point to another dynamic array, which will actually contain the elements which are contained in that particular bucket. So moving on, I think the first function we should focus on, now that we know sort of a high-level description of what each of these things does, we will look at hashmap create. So hashmap create, here is what it does. So we want to return to it the actual hash map we just created dynamically onto the heap. So of course, the first thing we do is we do a malloc, size of a hash map, because that's how much data we're allocating. We want to make sure we do a memory check just to make sure it's not null. And let's look at the arguments. So hashmap compare is just a function pointer, and if we give to it null, we will already assign to it a default compare function, which is just their standard string compare. And otherwise, we assign to it a user designated compare function. And the same logic applies for this default hash. We already have a default hash, which is sort of a very rudimentary hash. You could add more efficient and elaborate hashes that would give you a cleaner distribution that's more random, because there might be a tendency for the bins to prefer one bin over the other, just if the hash function that's used is not like uniformly distributed. And this gets a little bit potentially convoluted. I know it took me a while to get it, but we have remember that this is a structure which we need to designate a pointer to the buckets, which is a pointer to a dynamic array. And here we create this data structure called the dynamic array. And for now, just imagine that it's an array that contains data of some sort, and we can ahead of time designate how many elements we want this array to have. In this case, this array will point to another array. Remember, because it's the buckets. The buckets themselves, what do they do? They contain, or in this case, they point to another array which is dynamic, because as we start appending items onto the bucket, we start populating that bucket with, like, say, employee information. And we want it to be, the first layering is the size of this, which is set to 5, but it can be set to anything. So now what's the next thing? The next thing is the count of the buckets. So you might realize that this is actually dereferencing an element from the dynamic array, and one of the members of that structure is the count, which indicates how big is this dynamic array gotten so far. And notice that I put fake out expanding it, because by default, dynamic array starts with the size of 0, because it's an array that hasn't been populated yet. But in this case, we're actually saying, like, we've already populated it, don't worry about it. That's kind of what this is saying. I hope that makes sense. It's a little by the way, you'll have access to this on GitHub, so if you have, like, more questions, then knock yourself out. Okay, cool. Moving on to the next part. Okay, so the next implementation we will be talking about is set. Hashmap set, actually. And so once we've already created our map, which is one of the arguments, the user of this library will want to associate a particular key with some data. For example, as I've been using this example numerous times now, max with say employee data, which would consist of, like, a struct with employee information. And so how do we actually do? Well, one of the main things is we get the hash value, or the hash code that I've been talking about. We apply it onto this hash function. We get the actual value. we distribute it onto the number of buckets so that we get the element. And by element, I mean like the first layer is a dynamic array pointing. Each element will point to its respective contents of that bucket. So the bucket points to the elements inside that bucket is basically what I'm saying. And once we have the element number, then on the actual map, which its first layer consists of the actual buckets, we want to say, okay, well, what's in that bucket? Has it already been populated before? Or do we need to create it, right? Do we need to create the actual dynamic array that contains the data of it? So we get the bucket, right? And then we already anticipate that because we're creating a new data member, we anticipate that by creating a hash map node, which is basically like, what is the name of what's the key and what's the data associated with that key. If the bucket is null, then that means that this current bucket has not been initialized. So that means that we need to create the dynamic array, which contains the actual elements of that bucket. So for example, if max has a hash value of 3 and that third bucket has never been initialized before, then we create a dynamic array, and then we do a sort of initialization into it, and then finally we set the element, which would be the arguments are like at what place, right, and which bucket are we referring to, and that's pretty much it. So now let's actually see this run. So I am going to open the unit tests file. So here we have an array of structs. Each struct element represents the actual employee name along with its data. Here data is just simplistically an int, but keep in mind that this int could be replaced to be a structure, and that structure can contain, as many complexities as necessary depending on the particular application. So now you can see here that for each name, employee name, I have its data, which again is an int. And the first test we run is create the map. We pass to it null because we're going to let it use the default hash function, and we're going to let it use the default compare function. Once that test passes, we're all good. We're going to then test the appending onto it, and we can see that we're iterating this structure, right, with the name, because the name is, remember that hash map set, its second argument is the key, which in this case is the name of the employee, which is a string. The third argument is the actual data. So that's why you can clearly see here that we have name, and then we have data. And then here is the map that was created in the first test, which is actually, let me go to its definition. Tag not found. That's brilliant in a moment like this. Anyway, here it is, and we have a it's global variable for now, and that's why we can go ahead and reference that map when we're appending into it. And by the way, all of these tests have passed, at least so far. I tried my best to break it, and the times I did, I went ahead and fixed it. So for now, it should be good. And after we want to make sure we can get each element. And once that's good, then everything passes. If these checks don't fail, this test passes. Else, we go to this a label, which is the error label, and then we return the string that it failed. So let's go ahead and see it work. So let's compile it real quick, and then let's run it. And boom, so we can see here we're running the tests. Let's go ahead and zoom into this. I realize this is rather small. So let's go ahead and zoom in. Okay, cool. So we can see here that bucket 0 contains the elements Monica, Paul, and Raul. Bucket 1 contains Rex, Taylor, Tomas, Luke, Alan, Lisa. Bucket 2 contains all these names, and so on and so forth. So that's what's cool, is that that's kind of that's the printout of Traverse, and this kind of shows like, hey, these are all the contents of this hash table, and for each bucket, these are the contents within it. And these could not find node are actually on purpose. What I did is I removed a node. Say for example, if I remove David, and then I search for David, I shouldn't be able to find it. And me not being able to find it is actually a good thing, because it means that I removed it successfully, and or that I wasn't able to find it because it's not there. And you can see all test passes. And the code is on GitHub, so take a look at it yourself. If you can look at it into more detail, and then if you have any questions, or if you want to add any more features or enhance it in any way, please do so. So thank you all for your time.